Alrighty, so we are in A. Oh gosh, what? No, stay in ped mode. AB level 1. I believe we're at D now. Okay. So, AP Chem test prep level 1D. So last time we started talking about electron configuration. And how the element / atom is set up. Okay, so we also know that an atom contains protons, which are positively charged, and electrons, which are negatively charged. We learned from a while ago, and were reminded last video, that these charges are apart from each other and in certain energy levels. Okay? So we have certain energy levels, we have certain electrons and protons interacting with each other, and so if we have positive and negatively charged particles interacting with each other, they follow Coulomb's, I think I spelled that wrong, law. Okay? I did spell it wrong. It is C-O-U-L-O-M. There we go. Coulomb's law. And this is an equation that tells us the force, the electrostatic force required when there's a particle 1, a particle 2, and the radius, I believe it's radius squared. There we go. Okay, so the force between two particles, their charges are Q1 for the charge of particle 1, and the charge of particle 2 is Q2. And then it is inversely, or sorry, as the force increases, yes, so it's inversely proportional to the radius, or how far apart these particles are. So there's a stronger interaction between the, I'll use a different color here, electron in energy level 1 and the protons in the nucleus, because there's a shorter radius than electron number 2 and that radius. Okay, so there's a stronger force in the purple than there is in the red. Okay, now this sort of force and this separation into energy levels is the cause of, I guess just the cause of a lot of periodicity. Okay, so when we look at periodicity, which is trends in the periodic table, there are trends in the periodic table based on how it is arranged. Okay, I wish I could just like copy and paste a picture of the periodic table in here. However, I'm just going to draw a simple periodic table here. That's not right. There we go. Okay, and we'll throw the lanthanides and actinides in there for kicks and giggles. All right, so we have our basic periodic table here. The periodic trends that we can find are ones of metallic properties. Okay, so how shiny it is, the size, what else? Size, electronegativity, and electron affinity. Okay, so we'll do metallic properties in blue. Okay, the metallic properties of an atom or an element increase as you go down and to the left. So francium right here is our most shiny metal that we could probably find. It's synthetic, it doesn't stay around for that long, but if it did, it would probably be a very, very shiny metal. Okay, ironically, size follows the same pattern. Okay, so francium would be the largest atom as well. Electronegativity, okay, that is a different direction. Electronegativity actually increases as we go up the periodic table and to the right on the periodic table. So negating the actual noble gases, fluorine is the most electronegative element in the periodic table. All right, and as a quick reminder, electronegativity is how much an element would like to get an electron. And I know it's incorrect. We can't think of elements as like things that have their own attitudes or personal wants and needs. They aren't people or living beings. But it's easy to sort of explain it that way. So then that is different from the electron affinity, because the electron affinity is how much energy would be released if a electron were to be added to a neutral atom of that element. Okay? So the electron affinity has this trend. It is the same trend as the electronegativity. Okay, so electron affinity increases up and to the right on the periodic table. Okay, now all of these can be explained through the electron configuration of the elements. Okay, everything in the halogens, they are very close to having a full outer shell, and so their electronegativity, their want for electrons would be higher. Okay, they want that full shell. Like again, speaking in terms of ease of use, not electrons and elements do not want things, but they are more stable when they get that full energy shell, and so that's what happens. So it makes sense that they would have a high electronegativity, as well as the electron affinity. There should be a lot of energy released if those elements were to gain an electron, because they would be more neutral, or not neutral, they would be more stable. That's the word I was looking for. Okay, size, if we go down into the left, they have more, or they have, like, as you go to the right of the periodic table, not only are you increasing the electrons, but you're also increasing the protons. So you're increasing the positive charge in the nucleus. So that nucleus is going to be pulling those electrons towards it stronger, with more charge, than something that is all the way on the left, because it has fewer protons. Okay, and then as you go down the periodic table for size, you're increasing the amount of core electrons, which means they are shielding the outer electrons from the positive charge of the nucleus better. And so they're able to expand out further. There's less of a Coulombic force on those outer electrons. Okay? So these periodic trends are important to understand, important to go through, and they can help you sort of identify polarity of molecules. They can help you identify what molecule you have based on like electron affinity. So if you like lose an electron, what energy is released, that can show you sort of where in the periodic table your element is. So they can be very useful. Now there's one more trend that I wanted to look at. It's very, very similar to electron affinity. It is the ionization energy. Okay, it has the same trend. So the ionization energy is if you're going to be removing an electron, making an ion out of it. The amount of energy it would take to remove that electron should increase with the increased electronegativity or electron affinity, right? The ability for that electron to hold on, or sorry, that atom to hold on to that electron increases as you go up and to the right. And so if fluorine here is holding on to that electron very tightly, it wants to keep it, then when it loses that electron, it's going to take a lot of energy to do that. Okay? So that is the last trend I wanted to point out. Now, the ionization energy, the electron affinity, it all comes back to these energy shells and the Coulombic forces. Okay? So we know that atoms can be approximated to be in energy shells like this. Okay, you have your nucleus in the center, and then you have your energy shells with electrons inside them. Now, when we look at photon spectroscopy, we can determine what element we have, what atom we are dealing with, based on the photons that are released. Okay. Now, what we do is we end up throwing some energy. We'll put that in lime green because it's very bright. Throw some energy at an electron, or sorry, at an atom. One of those electrons is going to get excited. It's going to go up to a different energy level. So let's say it goes here. Okay, it goes out into the third energy level, and then eventually that electron is going to settle down. It's not going to have as much energy, and so it's going to relax back down. The nucleus is going to pull it back down to a lower energy level. Let's say it goes here. Okay, so once it relaxes back down and it gets pulled away, that energy has to go somewhere. And so that energy gets released as light. Okay? Now, we have talked about these energy levels. They have specific spacing to them, right? Their specific spacing is important because that can tell us what type of element we're using based on the light that's released. Okay, light has a certain energy. Okay, light has a certain energy. When it gets released, that energy, big word coming in, is indicative. I don't know if I'm going to spell this right. Indicative, probably not, of the energy shell spacing. Now, each element has its own individual spacing. Okay? So, through photon spectroscopy, we can figure out what element we're dealing with based on the energy shell spacing. Okay? That's what a photon spectroscopy is used for. Okay? Now, we're coming up on around 15 minutes. I don't want to get this, I don't want this to be a super long video, but we have one more topic to understand in dealing with periodic trends, and that is ions and valence electrons. Okay? Now, if we go up to our periodic table, we can see that we've got certain sections. We've got columns, sections, 1, 2, 3, 1, 2, 3, 4, 5, 6. Perfect. All right. So, these columns that I just made, they are called groups. Groups equals columns. Okay? Groups equals columns. Now, these columns can be indicative of the number of valence electrons an element has. Okay? It's very easy to tell for the s and the p orbital areas. For the transition and the lanthanides, it's a little bit more difficult to tell how many valence electrons they have. However, for the periodic trend here, group 1, group 2, 13, 14, 15, 16, 17, and 18. Okay? The final number in each one of these tells you how many valence electrons are in these elements. Okay? So every element in group number 1 has 1 valence electron. Every element in group number 2 has 2 valence electrons. Every element in group 13 has 3 valence electrons. 14, 4, 15, 5, 16, 6, 17, 7, and the noble gases 18 have 8 valence electrons. Now, when we're talking about ions and what ionic forces can be created, we need to look at their valence electrons. Now, every element, I'm speaking in terms of ease of use, every element is more stable when it has its 8 electrons in its outer shell. Okay, valence electrons, it wants 8. So, something like francium here, it has 1 valence electron. Now it has all of these other electrons back here. It doesn't just have the 1 electron in it. It's got a whole bunch of other electrons present. So, if it just loses 1, then it won't have all these empty spaces to fill. So, it's just going to lose 1 electron. It'll have a full valence shell then, and life is going to be simple. Okay? So, it's going to form francium. I almost spelled it out. Francium plus 1. Okay, it loses that negative charge. It was neutral before. So if it loses a negative charge, it has an excess of positive charge from 1, of 1. And so it's going to be francium plus 1. And so anything in the 2 column would lose 2 electrons, and calcium is in the in group 2, and so it would be calcium 2 plus. Then as we go forward, transition metals are different, so we don't worry about the transition metals right now. Transition metals are different. But if we go into group 13, it'll be a lot easier for these things to lose 3 electrons than it would be to gain 5. And so it's going to lose 3 electrons. Aluminum is in this group, so it would be aluminum 3 plus. Okay, group 14 is a little different because it can go either way. It can gain 4, lose 4. These tend not to form ions very well. Group 15, it's a lot easier to gain 3 electrons than it would be to lose 5. And so it's going to gain 3 electrons. Nitrogen is in this, and so it'd be nitrogen 3 minus. 16 is oxygen. Oxygen's in there, and so it would much rather gain 2 electrons. So an excess of negative charge. And fluorine would gain 1, making it a negative 1 charge. All right. So that is it for this level 1 talking points. Okay, this is all very, very quickly done. There's more information in these chapters, in these sections that you need to know. This is just a review to get you guys your mind jogging on the important aspects of this sort of level, this chapter. Okay, so I am in no means trying to teach the entirety of these topics to you in this short amount of time. However, take the notes, remind yourself, and then it might help you study going back and forth through your notes, textbooks, stuff like that. Okay? Stay healthy, good luck on the test, and we will go into level 2 next time.